of pharmacokinetics involves drug elimination. Drug elimination, there's two main ways that we can eliminate drugs. That would be biotransformation, in other words, liver metabolism to eliminate the metabolites, or renal excretion. The liver and the kidneys are clearly the two most important organs for drug elimination. They're not the only organs, but they are the two most important ones. When we talk about elimination, we use the term half-life. Easy to define half-life. Half-life is the time that it takes to decrease the plasma level to 50% of a former level. So we have to discuss half-lives as we're talking about drug elimination. There are two types of elimination. There's zero order and first order. Now, zero order is the exception to the rule. In other words, very, very few drugs are actually eliminated by zero order kinetics. When I think of zero order, make sure you highlight that it's a constant amount of drug that's being eliminated per unit time. A constant amount is the key thing. Also notice this, that drugs with zero order elimination have no half-life. They don't have a consistent half-life. Maybe another way to say that is that half-life has no meaning with zero order because it's not constant. The half-life is actually changing with zero order elimination. So you really can't use that term effectively as you describe zero order kinetics. When you think about zero order, think about these three drugs. They're listed at the bottom of the slide: ethanol, phenytoin, and salicylates. But when I think about salicylates, I'm pretty much going to focus on aspirin as the primary drug here. My phrase to remember those three: take the first letter of phenytoin, ethanol, and aspirin, and you can come up with this phrase that says 0 P's for me. 0 for zero order kinetics, P's, P phenytoin, E ethanol, A aspirin, 0 P's for me. It's a way to say, hey, I don't like P's. 0 P's for me. Those are your three zero order kinetics drugs. But it turns out that it's not all doses of those drugs are zero order elimination. Take phenytoin, for example. It's only the high therapeutic doses of phenytoin that are going to be zero order. Lower doses of this drug are actually first order. If you look at aspirin, it's only aspirin overdose where you get into zero order kinetics. The therapeutic doses of aspirin are all going to be first order. So you have to overdose on aspirin to get to that zero order state. Ethanol is the one of the three. Here's the phrase that we use. We say all reasonable levels of ethanol are zero order. That's the part that always bothered me. Reasonable. I mean, what's reasonable to you may not be reasonable to me, or what's reasonable to me now is probably not the same as what was reasonable to me 20 years ago. What that really means for us is that it doesn't take much ethanol to saturate the enzymes that are involved in elimination and put it into zero order kinetics. If you look at the box on this slide that says "in a nutshell," it's a reference over to page 13, kind of reminding us that zero order kinetics is going to happen when you saturate elimination mechanisms. Most doses of ethanol can do that. Only the high doses of phenytoin can do that, and only the toxic doses of aspirin can saturate those elimination mechanisms, which means your enzymes involved in elimination are working at Vmax. It's always great to have an example of zero order elimination. If you look at this slide and you start with 80 milligrams of a drug, after 4 hours, we're down to 70 milligrams. 4 hours later, we're down to 60. 4 hours later, we're at 50. And then 4 more hours, we're down to 40 milligrams. Check the amount. How much drug do we lose in the first 4 hours? We lost 10 milligrams. How much in the second 4 hours? Also 10 milligrams. In the third 4 hours, 10 milligrams. And in the fourth period of time, we lost 10 milligrams. We are losing a constant amount per unit time. We're losing 10 milligrams every 4 hours. So if I'm ever given numbers like this, very easy to tell if I'm dealing with first order or zero order. I simply look at the amount that I'm losing per unit time. You might also see zero order kinetics represented graphically. When we look at the graph on the left, we're plotting time versus units of drug on a linear scale. Both time and units of drug are plotted on a linear scale, and I get this type of linear decay. The graph on the left is probably the one that you're more familiar with, whereas the graph on the right, which plots time on a linear scale versus the log units of drug, this is a semi-log plot. This one is probably not as familiar to you. You get this type of curve here showing elimination involving zero-order kinetics. So probably more likely to see the graph on the left, but be aware that there are different ways that we can plot zero-order kinetics. With first-order elimination, it's not a constant amount of drug, it's a constant fraction of drug that's eliminated per unit time. Once again, highlight that phrase. Constant fraction is being eliminated. In fact, this is what most drugs are going to follow. Most drugs are going to be eliminated by first-order kinetics. In fact, we can pretty much go with the rule that if it's not phenytoin, ethanol, or aspirin, it's going to be eliminated by first-order kinetics. And in this case, we're going to follow typical enzyme kinetics. And what I mean by that is we're not saturating the enzymes. If zero order is really saturation kinetics, then first order is non-saturation kinetics. The enzymes are working at less than Vmax. Only in first order can we use the term half-life, because half-life is a constant in first order elimination. Once again, it's good to have an example. Here for first order elimination, we start with 80 milligrams, but we're actually told that the half-life of this drug is 4 hours. So every 4 hours in this graph, we're seeing the levels be cut in half. We go from 80 down to 40 in 4 hours, 40 to 20 in 4 hours, 20 to 10 in 4 hours, and then 10 down to 5 milligrams in 4 hours. But let's check the amount. How much drug is lost in that first 4-hour period? It was 40 milligrams. In the second 4-hour period, it was 20 milligrams. In the third period, it was 10 milligrams. And in the fourth period, it was 5 milligrams. The amount is changing. It can't be zero-order kinetics. This is first order. The amount is varying, but the rate is the same. You're seeing a constant fraction, which is the drug levels are being cut in half each time period. There are two ways to check what type of kinetics that you're dealing with. Number one, check the amount. If it's constant, if it's the same amount, that's zero-order kinetics. If the amount is changing, it's first order. The second way is to check and see if you have a consistent half-life. Here, we have a consistent half-life. Every 4 hours, the levels are being cut in half. At the bottom of my slide, I've got a couple of practical ways for you to use the concept of half-life. Practical as opposed to, say, doing a mathematical calculation for half-life. The first example says, what if a patient is dosed with 80 milligrams as shown in this diagram? Can you answer how much drug is left after 4 half-lives? It's a fairly easy question, simply asking you to decay the drug 4 times. The first decay goes down to 40, the second to 20, the third to 10, and the fourth takes you to 5 milligrams. After 4 half-lives, you have 5 milligrams left. What if we went the other way? What if you have a patient that shows up at the ER and you measure and find that they have 5 milligrams of drug in their body? The patient said she dosed 8 hours ago. How much drug did she ingest? Well, if she's got 5 milligrams now, I have to back up 8 hours, which is 2 half-lives. So I'm going to have to double that amount twice. The first 4-hour period, if you go backwards, 5 goes back to 10. The second 4-hour period, 10 goes to 20 milligrams. She ingested 20. That would be the correct answer to that question. You can also look at the graphs for first-order kinetics. Again, I think the graph on the left is the one that most people are familiar with. It plots time versus units of drug, both on a linear scale. And you get this type of exponential decay for first-order kinetics. Here's the scary thing. Look at the graph on the right. If I plot time versus the log units of the drug, notice how I get this linear decay that reminds me of zero-order kinetics, plotted on a linear scale. So the similarity between those two graphs is a point of concern, no doubt. It means really a couple of things. One, it means you might have to pay attention to your axes. Is it units of drug or is it log units of drug? The second is, how about if there's another way to distinguish what type of kinetics I'm dealing with when I look at a graph? That other way would be to determine half-life of the drug. We're going to do that on the next slide. So in this graph, we're plotting time versus plasma levels of the drug. In this type of graph, we can actually estimate half-life. And if I can estimate half-life and get a consistent half-life, I know that I'm dealing with first-order kinetics. I know that that's what I'm dealing with. You should notice by the shape of this curve that it's an IV dose. Do you notice that the plasma levels start up high and then follow with the elimination phase over time? In fact, when you look at the graph and you carefully analyze, there actually are two slopes shown here. The first slope is the distribution phase. It's very short. Time-wise, it happens very quickly. That first slope represents the drug being distributed from the plasma into the tissues. The second line, the second slope, is much longer and represents the elimination phase. Here's a rule for you to follow. If you're ever going to try to estimate the half-life of a drug from a graph like this, you always want to look at the elimination phase in order to do your estimation. Choose plasma levels that will correspond to a portion of the elimination phase. Never use those higher plasma levels that correspond to the distribution phase. So to estimate half-life, first I'm going to pick a number. Let's say I pick a plasma level of 4. I follow 4 over until it intersects with my line. I come down to the x-axis and I read 3 hours. I make a mark right there. The question really is, how long does it take to go from a plasma level of 4 to a plasma level of 2? Let's follow 2 over to the line. When I follow 2 all the way across to where it intersects with my graph, and then I come down to the x-axis, I make a mark at 6 hours. The difference between those two lines, from 3 to 6, is 3 hours, and that is an approximation of the half-life of the drug. So once again, I can use a graph to estimate half-life. And if I wanted to, I could repeat that and find out if I get a consistent half-life. If I do, that's first-order kinetics. If I don't get a consistent half-life, that would be zero-order kinetics. When it comes to renal elimination, the rate of elimination is a function of GFR plus how much of the drug was actively secreted minus how much of the drug was reabsorbed, either actively or passively. So GFR plus secretion minus reabsorption. When you think about renal filtration is a non-saturable linear function. We've learned earlier that both ionized and non-ionized drugs can be filtered, but protein-bound drugs cannot. Clearance is constant in first-order kinetics. In fact, clearance is equal to GFR when you don't have reabsorption or secretion, as well as no plasma protein binding. It doesn't really sound realistic, though, because many drugs are bound to plasma proteins. So I have to think about clearance being a function of the free fraction of the drug. In fact, it's the free fraction multiplied times the GFR that will estimate the clearance of the drug. But free fraction is not something that is commonly given to you in a question. What are they more likely to give you in a test question? It will give you how much of the drug is bound to plasma proteins. So simply take 100% minus the percent bound to give you the free fraction. If a drug is 80% bound, then 20% of it is free. 20% times my GFR gives me the clearance of that drug. Once again, only the free portion of that drug is being filtered and cleared from the body. But let's do some interpretation here. It's very important for you to actually see numbers and explain what those numbers mean. What if you're told that the actual clearance of a drug is less than GFR? The clearance is less than GFR. You have to assume that what process is going on. If the clearance is less than GFR, then I must be reabsorbing that drug. I filtered a certain amount, but that's not what I'm eliminating. I'm eliminating less than that. So I must be reabsorbing the drug. On the other hand, if the actual clearance of the drug is greater than the GFR, then I must be adding to the filtrate. I must be actively secreting that drug into the renal tubules, because what I filtered is not as much as what's being cleared, so I must be adding to the filtrate at that point.